Let's explore this idea of redundant vectors further. It's going to be an important idea going forward. When we deal with a span of vectors, it turns out it's going to be easier to describe the properties of that span if the spanning set doesn't include any redundant vectors. So we want to be able to know when we have and when we do not have redundant vectors in a spanning set. Okay, so let's prove a theorem. This is going to be one of the more important theorems that we look at in this class. So let's consider a set of vectors, v1, v2 to vk, that are n-dimensional vectors. And we want at least two of them, so k is greater than or equal to 2. Then the following are equivalent. Following conditions are equivalent. A, the set of our vectors v1 to vk contains a redundant vector. At least one. Could contain more than one. So if that's true, it turns out that we also have the following property. The system C1v1 plus C2v2 all the way to CKVK equals 0. Okay, so specifically a linear system that is equal to all zeros on one side. Okay, the system C1v1 plus C2v2 plus CKVK equals 0 has a non-trivial solution. What does that mean? Okay. So notice this clearly has a solution. And by solution here, I mean the values that we could choose for the scalar multiple c. Okay. Now, clearly, no matter what the vectors v are, there are values of c that we could choose to make this equation true. We could choose all the c's to be the scalar 0, right? And then this equation would be true. That's called the trivial solution. Because it's trivial, it's obvious, it's easy. Okay? Clearly this has that one solution, so that's trivial. We're interested in, are there any other solutions? Any solutions where not all of these constant scalars are 0? That would be a non-trivial solution. That is there is a solution where at least one of the c's okay, and c, condition c, one of the vectors can be expressed as a linear combination of the others. Okay. Now, we want to prove that all of these conditions are equivalent. That means if any one of these conditions is true, then they will all be true. Okay, all of these mean the same thing. Essentially, we're just talking about them in different ways. Okay. So this proof is going to be a fair bit of work. So let's get started. To start, I'm going to assume condition A is true, and I'm going to show if condition A is true, then condition B must also be true. Okay, so I'm showing that if A is true, then B is true. Okay, so we're going to start by assuming that our set contains a redundant vector. So suppose the set v1, v2 to vk contains a redundant vector. Say vj. So one of the vectors in the middle. So j, it might be 1, j might be k, but more likely it's one of these vectors in the middle here, right? Somewhere in there we have a redundant vector. Okay, so now let's apply the definition. What does it mean to have a redundant vector? Then by the definition of a redundant vector, the span of all the vectors, including the redundant vector, hiding somewhere in here in the dot, 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 is equal to the span of the same set of vectors, but with the redundant vector removed. Okay? So I get the same space. The sets are equal. But here, the VJ was in there somewhere. Okay, hiding in the dot, dot, dots. But here we very clearly said, nope, it's gone now. We have the vector before it, we have the vector after it, but now it's not there. Okay, VJ isn't there. The redundant vector has been removed. Now we want to show that B is true. We want to show that if we look at this system and set it equal to 0, that we have a non-trivial solution. We can choose the C's so that they aren't all 0. Okay, we're going to do this a clever way. We're going to do it by taking some vector and expressing it as a linear combination in both of these spans of vectors. Okay, so let's let vector W equal to v1 plus v2 plus dot, 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 and somewhere in there's vj, remember, plus dot, 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 plus vk. Okay, so I'm choosing W to be that. That's what I'm calling W. Notice that W then is in this span, right? Because this span contains all linear combination of the vectors V. And that's exactly what this is. This is a constant 1 times V1 plus a constant 1 times V2, and so on. Okay? But this span of vectors is equal to this span of vectors. Okay? So let me actually write that out, which is in the span of V1 to V2 to Vk. Okay? It's in here. But since the spans are equal, I must also be able to express W as a linear combination of these vectors. But since the first span equals the second span, okay, right? Just restating this. But that's the reason why this is going to work. We can express W as a linear combination of these vectors right here, okay? The vectors without the Vj. Say we write W as B1 V1 plus B2 V2 plus dot 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 plus Bj minus 1 Vj minus 1 plus Bj plus 1 Vj plus 1 plus dot 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 plus Bk Vk. Okay? Notice I don't know what the B's are. I don't need to know. But I do know that because W is in this span of vectors, I can express W as a linear combination of those vectors. That's what it means to be in the span, right? We are just using the definition of what it means to be in the span. So I have two different ways to express W as a linear combination of the vectors in V. Okay, I have this way that I chose first, and then I have this way, which I know must exist, where Vj isn't in here. Subtract the two linear combinations. To get, so now I'm going to take this and I'm going to subtract this, okay? Now on the left-hand side, vector W minus vector W is 0, is the 0 vector. On the right-hand side, subtract corresponding terms. V1 minus B1 V1 is 1 minus B1 V1 plus V2 minus B2 V2 is 1 minus B2 V2. And we're going to keep on doing that. And so for almost every element, we will have 1 minus the coefficient here of that element. So like VK, I'd have 1 VK minus BK VK, so I'll get 1 minus BK VK. But remember, there is one missing here, right? In between J minus 1 and J plus 1, I don't have any jth term. So when I take Vj here, I have nothing to subtract it over here. So I'll just have 1 Vj. Not 1 minus Bj Vj, because there's no Bj Vj in here. Okay? And so this is kind of the weird one out. All of the other vectors have this form, but not that Vj. Okay? Now, what were we trying to prove again? We're trying to prove part B here, that this system has a non-trivial solution, so that I could set it equal to 0 where not all of these coefficients are 0. Well, hey, look at this. This is equal to 0, isn't it? But what's the coefficient in front of Vj? Not 0. Now, I should say these might be 0, they might not be, because I don't know the value of B. I don't know if they're 0 or not. But I know that this one isn't 0. And that's what I need to show, that there's one coefficient here that I could set not equal to 0 and make this linear combination with this guy not 0 equal to vector 0. since the coefficient, or the, yeah, so the scalar coefficient of Vj is 1, which is not 0, the claim is proved. Okay, so what we've done here is we've said, oh, if this is true, then we have a non-trivial solution to this equation. Okay, and so we said if A is true, then B is true. And we've still got quite a bit of work to do. Next, we need to show if B is true, then C is true. Because remember, we want to show all these are equivalent. It's not just enough to show that if A is true, that B is true. I need to show if any one of these is true, that then all of them are true. Okay? So now what we're going to do is we're going to assume B is true and show that C is true. Okay? Now I will say I think this first part's the hardest part, so hopefully that makes sense. This next part should be a little bit easier. Okay? So we're assuming part B here, which is this system has a non-trivial solution. Suppose C1v1 plus C2v2 plus dot 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 plus CKvk equals 0, the 0 vector, has a non-trivial solution. So remember, a non-trivial solution means that one of these is not 0. So let's say with, say, the jth coefficient not being 0. Okay, somewhere in there, there's one that's not 0. I don't really care which one. Somewhere, pick the one that's not 0. I know it's there somewhere. Okay, because this has a non-trivial solution. Then do a little bit of algebra here. What I'm going to do is I'm going to subtract this to the other side of the equation. Okay? The term that has a non-zero scalar coefficient. So if this is true, it implies that C1v1 plus C2v2, and now I need to indicate that I've taken the jth term out. So I show the one before and the one after it. And instead, the jth term I've subtracted to the other side. Okay, so it was right here in between these guys. Okay, in between the j minus 1th term and the j plus 1th term, but I've subtracted it to the other side of the equation. Okay, now remember our assumption. We're assuming that Cj is not 0, which means we can divide by it. If it were 0, we couldn't divide by it. But because it's not 0, we can divide everything by it. And so if I divide everything by negative Cj, I get negative C1 over Cj V1 minus C2 over Cj V2 plus dot 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 plus Cj minus 1 over Cj Vj minus 1 plus Cj plus 1 over Cj Vj plus 1 plus plus ck over cj. I'm sorry, minus. I should be subtracting. I'm dividing by negative cj. So all these should be minuses. So negative ck over cj vk, that's going to be equal to vj. Okay? So just basic arithmetic, but it does look complicated only because there's so many symbols, right? But the arithmetic is actually simple. We just subtract it to the other side, and then we just divide by negative cj. All I'm doing is I'm solving for this vector, okay? The vector that has the non-zero coefficient. I'm showing I can do that. And now look what I have on this side. Negative c1 over cj, that's just a scalar constant. So I get a scalar constant times v1 plus a scalar constant times the next vector, scalar constant times the next vector, scalar constant times the next vector. This is a linear combination. So I have expressed vj as a linear combination of all the other vectors. Meaning we can write vector vj as a linear combination of the other vectors. And that's what we wanted to show. Part C is that one of these vectors can be expressed as a linear combination of the others. And that's what we did right here. Vector vj is a linear combination of these other vectors. Okay? We're almost done. We have one more part to go. Okay? We've shown that if A is true, that B is true. And if B is true, we've shown if C is true. What we want to do now is we want to go back around and we want to show if C is true, then A is true. And that will kind of complete the cycle here. If I could show that, then if A is true, then B is true. And if B is true, then C is true. And if C is true, then A is true. And I could just go around the cycle. And if one is true, they all must be true. Okay? So I'm just going to complete the cycle here. So I'm going to assume that if one vector can be expressed as a linear combination of the others, then we have a redundant vector. Okay, this is an idea that we have seen before. We've looked at particular examples, but now we're going to look at the general proof. Okay. Suppose one of the vectors v1, v2 to vk can be expressed as a linear combination of the other vectors. Say, in particular, maybe it's the jth vector, whatever j is, that can be expressed as a linear combination of the other vectors. So let's go a1 v1 plus a2 v2 plus plus, and I need to show that I've taken the jth vector out. Okay, so all I'm doing is I'm using the definition of what a linear combination is, right? And I'm just saying, hey, one of these vectors, I'm calling it vj, can be expressed as a linear combination of the other vectors. So scalar coefficient times a vector plus a scalar times a vector plus a scalar times a vector plus a scalar times a vector, and so on. Okay, that's what a linear combination is. Okay, so all I've done so far is state my assumptions. I'm assuming that one of the vectors can be expressed as a linear combination of the others. Now I want to show that this is true, that the set contains a redundant vector. Okay, specifically, we're going to show that that Vj is the redundant vector. Okay. Now take any vector w in the span. Okay, and this is all the vectors. v1, v2, all the way to vk, including hiding in here the jth vector, whatever it is. Okay, now what does it mean to be in the span? It means that we can write w as a linear combination of these vectors, right? Then vector w is equal to, say, b1 times v1 plus b2 times v2 plus ... Let's go ahead and get the jth vector in there already. Okay, because that's what it means to be in the span. It means you can be written as a linear combination of these vectors. Okay, but now let's use our assumption. Actually, let me put another equal sign here. We know that Vj can be written as a linear combination of these vectors. Okay, so what I'm going to do is I'm going to substitute this in for Vj. So I get b1 v1 plus b2 v2 plus ... bj, and then instead of vj, I'll have a1 v1 plus a2 v2 plus ... aj minus 1 vj minus 1 plus aj plus 1 vj plus 1 plus ... plus ak vk. Okay, so all of this is the same as vj, right? All I'm doing is substituting. And then at the end here I have plus bk vk. Okay, notice now vector vj is gone, right? It's gone. I've swapped it out with an expression involving the other vectors instead. So let's combine like terms. Okay, so I have a b1 in front of v1, and I also have a bja1 in front of v1. So if I combine those like terms, I get b1 plus bja1 times v1 plus, same thing for v2, b2 times bja2 v2. bja2 v2, and so on. Okay, just combine in like terms. Okay. Now notice what I have. b1 plus bja1, that's just a scalar constant, right? So I have a scalar times a vector plus a scalar times a vector plus a scalar times a vector plus a scalar times a vector, and so on. This is a linear combination. but it's a linear combination of the vectors that do not include vector vj. It's not one of the vectors in the linear combination, right? So this means W is in this other span. That doesn't have vector vj in it. Okay. Notice there was nothing special about vector w. The only thing we assumed about vector w is that it was in the original span, okay, which includes vj. So we said, hey, if w is in this span, and what we did is we proved that it's also in this other span once we take out vector vj. So that means that this set is a subset of this set, because everything in this first span, every vector w that we could choose, any one of them, would also be in this set. And that's what it means to be a subset, right? But notice the opposite's also true, right? Any linear combination of these vectors could obviously be expressed as a linear combination of these vectors, because all of these vectors are in here. This just has one extra. It just has that vj. So what we've done is if this is a subset of this set, and if this set is a subset of this set, then they must be equal. Therefore, the span of all the vectors is equal to the span of the vectors with the jth vector missing. Meaning that that jth vector is redundant. Remember, this is what it means to be redundant. If we take it out, we get the same span. And that's the last bit of the proof. Okay, we've proved all of these. We've shown that all of these are equivalent. If any one of these is true, all of them are true. All right. Okay, I know this was a lot. Linear algebra can be a bit like this, death by symbols. There's a lot of symbols floating around here. Try to not focus so much on the individual symbols. Try to focus on the main arguments. Okay? Try to see the big picture instead of all the little pieces.